Friends, today we're going to discuss Unit 5 rotor design of three-phase induction motor in the subject of design of electrical machines. The topics of our discussion will be combination of stator and rotor slots, rotor bar currents, area of rotor bars, shape and size of rotor slots. The suitable combination of stator and rotor slots requires following important combinations. We need to consider the effect of crawling, that is seventh order harmonics. It is also known as the harmonic induction torques, cogging, which leads to magnetic locking, also known as harmonic synchronous torque, vibration and noise. So here we are saying that we are having two main parts of the three-phase induction motor, a stator and a rotor. The stator is the stationary part, which consists of a core having slots in the inner periphery. The slots carry the three-phase AC winding, which produce the magnetic flux when three-phase AC supply is given to the stator. This rotating magnetic field, which is produced by the stator windings, is linked by the stationary rotor and thereby inducing EMF in the rotor according to Faraday's law of electromagnetic induction. This rotor winding or rotor bars will have current flowing through them. The direction of this current is given by the Lenz's law. These currents will also produce the flux, and there will be an interaction between the stator flux and the rotor flux, which will lead to the production of torque, because the basic principle of the motor is current carrying conductor placed in a magnetic field will experience a force. So the torque which is being produced by the motor will be on the current flowing in the stator and the current flowing in the rotor, and their fluxes which will interact with each other. So this combination of stator and rotor slots will decide the value of the torque or output power available to the motor. So we must be in a position to select a suitable combination for the stator and rotor slot, which is the objective of this lecture. So what is the effect known as crawling? When three-phase AC supply is given to the stator, this three-phase AC supply consists of large amount of harmonics. Harmonics are nothing but the multiple frequency components of the fundamental which are produced in the system. These harmonics can be even order harmonics or odd order harmonics. Mainly, the effect of odd order harmonics are more predominant than the even order harmonics, because even order harmonics generally tend to cancel out each other. The odd order harmonics, specifically talking about the fifth and the seventh order harmonics in the three-phase induction motor, will produce two different types of torques. The fifth order harmonics are having a rotating magnetic field which is in the opposite direction to the fundamental frequency rotating magnetic field, whereas the seventh order harmonics will produce a rotating magnetic field which is in the same direction as that of the fundamental rotating magnetic field. So here the three torque speed characteristics will be are demonstrated in this graph, which will be due to the fundamental torque frequency, the seventh order and the fifth order. So you can see here the fifth order is in the opposite direction, whereas the seventh order is in the same direction. Now the fifth order harmonics, since it is in opposite direction, it will tend to reduce the overall torque, but the seventh order harmonics is of more importance here, because the seventh order harmonics will tend to produce, if you see the resultant torque will be having a dip here. So the seventh order harmonics will lead to torque which will be developed at the seventh of the synchronous speed, which will lead to a reduction in the value of the torque. So the motor at this particular point, at the 1/7 of the synchronous speed, will have very low value of torque, and if the low torque at that time is higher than the torque produced by the motor, then the motor will have a tendency to run at a speed which is 1/7 of the synchronous speed. So this effect of reduction in the speed, or the motor attaining a speed 1/7 the synchronous speed, is known as the crawling. So the motor has a tendency to crawl at 1/7 the speed. This effect is also known as the harmonic induction torque. So this harmonic induction torque will lead the motor to run at 1/7 the synchronous speed. This effect is known as the crawling. So we must have a combination of stator and rotor slots such that the effect of crawling does not take place. Similarly, there is also one more effect known as the harmonic synchronous torque, or in other words, the effect harmonic synchronous torque leads to an effect known as the cogging. So basically, the stator and rotor harmonics are of the same order. They will produce torque which will be alternatively opposite. As we have seen, the 5th and 7th order harmonics, they produce torque in the opposite direction. So similarly, stator and rotor harmonics will also produce the torques which will be alternatively opposite. If the speed of the rotor magnetic field and the stator magnetic field due to harmonics, if they coincide with each other, there will be occurring a magnetic locking. This can be also be explained that we know that the motor has stator poles as well as the rotor poles. So if the rotor poles and stator poles align with each other, there will be minimum reluctance between these two poles. So they will produce a locking effect, and they will develop a synchronizing torque. So the motor will work as a synchronous motor. So instead of running at different slip, the motor will run at a slip which is equal to 0. So the motor will get converted as a synchronous motor, and it will run constantly at a synchronous speed. So this effect is known as cogging. This is due to the fact that there is a harmonic synchronous torque being produced. So we must also take into consideration these effects. Similarly, we know that if the number of stator slots and rotor slots, if are not taken into proper consideration, then there will be large amount of noise will be created because of the tooth pulsation. Losses being developed will be larger. So the air will be having larger obstruction, and that obstruction will lead to large amount of noise. So vibration will be also be produced due to this noise. So there are certain rules which are being laid down so that the rotor slots can be effectively be chosen. So we know that for having to reduce the harmonic synchronous torques to be produced or cogging to be produced, we must not have the rotor slots equal to the stator slots, because if rotor slots and stator slots match with each other, there will be a magnetic locking and the motor will run at a constant synchronous speed, which we did not need. So in order to reduce the effect of cogging, rotor slots should never be equal to the stator slots. Similarly, the difference between the number of stator slots and rotor slots should not be should be P, 2P or 5P. The difference should not definitely be 3P for the magnetic locking. For the to reduce the effect of magnetic locking, again we should not want the difference to be 3P. The difference should not be 1, 2, P plus and minus 1 or P plus and minus 1. So these are the some rules which are being laid down for selecting the rotor slots from the number of stator slots. So once we define the number of rotor slots, then we have to calculate the rotor bar current. So we know that so long as the motor is stationary, it is like a transformer where the stator MMF will be equal to the rotor MMF. So that is nothing but stator MMF is number of turns into the current is equal to the rotor MMF, that is the rotor current multiplied by the number of rotor turns. So, but what happens under running condition? Under running condition, due to the slip, the MMF of the rotor changes. We know that MMF is nothing but the product of current into the number of turns. when the rotor starts rotating, the rotor current changes due to the change in the value of rotor impedance and the rotor EMF, which both depend upon the frequency of the rotor, which changes when the rotor starts rotating. So hence we can say that the rotor MMF is some percentage of the stator MMF under running condition, and that basically depends upon the value of the slip. So we are saying that the rotor MMF is some percentage or mutual coupling factor into the stator MMF. Generally, if this value of mutual coupling factor is not given, we assume it to be around 85% of the stator MMF. So generally we consider 15% less than the stator MMF. So we can say that the MMF of the stator and the MMF of the rotor is can be given by this empirical formula: IB into SR is equal to KCM into 6 ISTS. So we can say that IB is equal to, that is the rotor bar current will be KCM ISTS upon the SR. So from this formula we can calculate the value of rotor bar current. Once we know the value of rotor bar current, we can select or assume a suitable value of current density, which is having a range from 4 to 7 ampere per millimeter square, so that area of the rotor bar can be calculated as AB is equal to IB upon DB in mm square. Now once we obtain this area of a rotor bar, we have to again see that this rotor bar's size is available in the market or not. So from the market we can select the available bar which is very near to this calculated area. Hence we can effectively manufacture the rotor bars. The area of the slot definitely will be greater than the area of the bar if we are assuming that we are using one bar in one slot. So definitely the area of the bar will be smaller as compared to the area of the rotor slot. So the area of the rotor slot will incorporate some amount of insulation. So the area of slot can be calculated by using the space factor of the for the rotor slots. So once we have calculated the value of area for the rotor bars, then we can select the size and shape of the rotor slot. So size can be selected by assuming a suitable value of the insulation requirement, and from there we can get the area of the slot. Where as far as this shape is concerned, the rotor slots can be either totally closed type or semi-enclosed type. Usually if we are having only one bar, then we can use a totally closed type, or if we are using thinner conductor, we can use semi-enclosed type also. Generally, in many of the times it is required that we require a high starting torque. For high starting torque, we need to use a deep rotor bar type of arrangement. So there we can use two different rotor bar conductors, one on the upper side, one on the lower side. So in order to improve the starting torque, we use deep rotor bar type of slots. So we can have a slot which is circular or taper type. So here some of the rotor laminations are being demonstrated. We can have any of these type of arrangement for the rotor slots. So this finishes up with the topic of rotor bars and slots. If you like this, please subscribe to this, and don't forget to place the bell icons. Thank you.